For decades, Mars has been described as a dead world. No rain, no flowing rivers, no active volcanoes. A planet where meaningful geological change should take millions of years to notice. Then scientists placed two photographs side by side. One was taken in 1976, when NASA's Viking mission became the first successful lander to operate on Mars. The other was captured nearly half a century later by the European Space Agency's Mars Express spacecraft. They were looking at the same place. It did not look the same. A vast dark region in Utopia Planitia had shifted by at least 200 miles on a planet where landscapes are supposed to remain almost frozen in time. The material moving across the surface is not fresh lava. It is not flowing water. It is ancient volcanic minerals that have remained in place for millions of years until something changed. Scientists know the change is real. They do not yet know why. The European Space Agency has proposed two competing explanations. Both fit some of the evidence. Neither explains everything. What makes the mystery even stranger is where it is happening. Utopia Planitia is thought to have once been the floor of an ancient ocean. It contains one of the largest known reservoirs of buried water ice on Mars. It is where humanity first touched down safely on the red planet, and now it has become the site of one of the most unexpected surface changes ever documented there. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. The story begins with a pair of photographs taken nearly 50 years apart and a discovery that challenged the idea that Mars has been standing still. Imagine placing a page into a book, closing the cover, and finding that page untouched after billions of years. That is the closest comparison we have for understanding Mars. As we continue across its surface together, it helps to stop thinking of this world as a landscape first. Instead, think of it as an archive where nearly every chapter remains preserved where it was written. Earth rarely grants that luxury. Flowing rivers grind mountains into sand. Rain reshapes valleys. Living organisms churn the soil. Continents drift across the globe, carrying pieces of crust into the mantle where ancient seafloors disappear forever. Even glaciers erase the marks left by earlier ages. Our planet is constantly revising itself, replacing old pages with new ones until much of its earliest history survives only in scattered fragments. Mars followed another path. Its crust never developed the global system of moving plates that continually rearranges Earth's surface. Stable bodies of liquid water vanished long ago. No forests spread across the ground. No oceans returned each season to wear away exposed rock. Even the atmosphere is astonishingly thin, exerting only about 1% of the surface pressure experienced on Earth. Dust can still travel, but the power to remake an entire landscape is greatly reduced. The result is extraordinary. Features approaching 4 billion years in age remain exposed beneath the open sky. Ancient lava plains, impact scars, dried river channels, and buried shorelines persist across enormous distances because almost nothing has erased them. When we examine Mars, we are often looking directly at events unimaginably older than the oldest surviving landscapes on Earth. That perspective changes how we should view the spreading dark patch. Here, a shift of roughly 200 miles across about half a century becomes far more significant than the same change would be on our own planet. Against the normal pace of Martian history, even modest movement stands out with unusual clarity. You are watching fresh handwriting appear on a page that almost never changes. There is another principle worth carrying with us. Volcanoes on Earth rarely remain above the same source of rising magma for very long. The crust keeps drifting, transporting each volcano away until its eruptions eventually cease and another mountain begins elsewhere. Mars lacks that restless motion. Its crust stays fixed above deep reservoirs of molten rock, allowing lava to accumulate in one location over spans of time that stretch beyond ordinary imagination. Over immense ages, that steady process produced volcanic provinces unlike anything found on Earth. Layer upon layer of molten rock gathered without interruption, building landscapes of remarkable scale while spreading dark minerals across neighboring regions. Those minerals would eventually become part of the surface record we are following today. Once you recognize Mars as a world that preserves rather than replaces its past, every dark deposit, every crater, and every exposed layer becomes less like scenery and more like a surviving page waiting to be read. From orbit, Utopia Planitia appears almost deceptively simple. Its broad expanse blends into the surrounding northern plains, so gradually that your eye could easily pass over it without noticing anything unusual. Yet beneath that understated appearance lies one of the richest geological records anywhere beyond Earth, a place where almost every major chapter of Martian history has left a trace. The basin stretches for roughly 2,050 miles from one side to the other. If you could lift it from Mars and place it across the continental United States, it would span the nation from coast to coast. That immense circle marks the aftermath of an ancient collision when an incoming object estimated between 250 and 430 miles wide slammed into the young planet more than 4 billion years ago. The impact excavated an enormous depression, permanently reshaping the northern hemisphere and leaving this basin among the lowest regions on Mars. Its story did not end there. Once the violence faded, gravity favored the deepest ground. Water naturally sought lower elevations, and growing evidence suggests that an ancient Martian ocean eventually collected within this vast hollow around 3,680,000,000 years ago. For hundreds of millions of years, this basin may have served as the floor of an inland sea, receiving sediments that drifted downward through the water and settled across the landscape below. Time continued adding new pages. Powerful volcanic eruptions from distant regions scattered dark ash across the northern hemisphere. Layer after layer accumulated over the basin, sometimes before the ocean existed, sometimes while water still occupied the lowlands, and sometimes after the sea had vanished. Dust gradually concealed much of that volcanic material, preserving it beneath younger deposits instead of sweeping it away. Another layer arrived through climate rather than fire. Beneath portions of Utopia Planitia rests one of the largest known reservoirs of buried water ice on Mars. Radar observations have revealed frozen deposits reaching as much as 560 feet thick, protected beneath rock and sediment for immense spans of time. The basin became more than an ancient seafloor. It also became a vault, preserving frozen remnants from a very different planetary environment. Now we reach the uppermost layer, the changing dark patch that first drew our attention. It occupies the surface above everything that came before, making it the latest visible addition to a record extending across more than 4 billion years. When you look at that shifting boundary, you are not seeing an isolated stain across empty ground. You are looking at the newest mark placed atop an impact scar, an ocean basin, volcanic deposits, and buried ice, all occupying the same remarkable location. Seen this way, Utopia Planitia becomes far more than a destination on a map of Mars. Every discovery here belongs to the same landscape, each resting upon older events that shaped the ones above. The expanding dark region gains meaning because of where it appears. It reflects a place where the deepest past remains stacked beneath the present, allowing one stretch of Martian ground to preserve an astonishing sequence of planetary history within a single basin. Some discoveries happen in an instant. Others spend decades waiting inside an archive until someone thinks to compare two forgotten images. The turning point in this story began with a photograph that seemed completely ordinary when it was first transmitted to Earth. On September 3rd, 1976, the National Aeronautics and Space Administration successfully landed Viking 2 in Utopia Planitia. It became the first spacecraft to reach the surface in this immense basin and only the second successful landing anywhere on Mars. While the lander examined its surroundings, companion spacecraft circling overhead mapped the wider landscape in remarkable detail for their time. Among those orbital views sat a broad, dark region contrasting against the familiar reddish plains. Scientists documented it carefully. Spectral observations and its appearance suggested ancient volcanic material, rich in dense minerals left behind by eruptions from a much earlier age. The feature received attention, then settled into the growing catalog of Martian geology. There was little reason to believe it deserved anything more. Mars already displayed dark dunes, wind streaks, and exposed volcanic rock in many places. This deposit simply appeared larger than most. What no one recognized was the true importance of timing. That image captured the landscape exactly as it existed in the middle of the 1970s. Without intending to, the mission created a reference point that future generations would inherit. You cannot recognize change without remembering what came before, and the Viking record preserved that memory. Nearly half a century later, on November 9th, 2024, the European Space Agency directed the Mars Express spacecraft across the same region. Its high-resolution stereo camera recorded the basin with a ground resolution of roughly 56 feet for each picture element, allowing researchers to compare modern observations with the historic Viking photographs. When those images were aligned, something unexpected emerged. The southern edge of the dark terrain no longer occupied the same position. Portions of the boundary had advanced by at least 200 miles across the surrounding plain. This was not the kind of variation expected from different camera angles or lighting conditions. The shape itself had changed. The comparison reached the scientific community in April 2026. Rather than announcing a confident solution, the European Space Agency offered unusual restraint. Researchers explained that the expanding volcanic ash could be interpreted in two physically reasonable ways, and then added an admission rarely heard in planetary science. At present, there was no evidence showing which explanation was correct. That sentence carried remarkable weight. An active spacecraft equipped with 13 scientific instruments had examined Mars for years. Decades of orbital observations already existed. Specialists across Europe evaluated the evidence with exceptional care. Even so, the mechanism behind this visible transformation remained unresolved. For you and me, those paired photographs become more than historical records. Together, they reveal that one small portion of Mars refused to remain exactly as earlier explorers left it, and that a world often described as unchanging still has the ability to surprise the people who continue watching it with patience. Before we ask, what is moving across Utopia Planitia, we first need to understand what is actually moving. The answer begins far below the surface of a planet, inside regions that no camera has ever seen directly, where extreme heat transformed molten rock into crystals long before they reached open ground. Planetary geologists describe the dark material as mafic, a word formed from magnesium and iron, the two elements that dominate its composition. Within this deposit, two minerals stand out above all others: olivine and pyroxene. Their names may sound technical, yet they reveal an extraordinary origin story written deep inside ancient Mars. Olivine forms when molten rock cools under tremendous heat beneath a planet's crust. On Earth, it makes up much of the upper mantle, the broad layer resting below the crust itself. We rarely encounter it at the surface, unless volcanic eruptions transport it upward from the interior. Every grain of exposed olivine represents material that once existed far below the landscape we can see. Pyroxene follows a similar path. It also crystallizes from intensely hot magma and commonly appears dark green or nearly black, dense and durable. It belongs to the same volcanic family as olivine. Together, they preserve a chemical record of Mars during an era when molten rock regularly reached the surface. That makes these minerals unusual. They did not originate where they now rest. They began deep inside the planet before powerful eruptions carried them upward and spread them across the northern plains. If you discovered comparable material scattered across an ordinary field on Earth, you would be holding fragments that once belonged beneath the crust itself. Their appearance also explains why this region stands apart from its surroundings. Olivine and pyroxene absorb much of the sunlight, striking them instead of reflecting it back into space. The familiar reddish color covering most of Mars comes from extremely fine dust coated with iron oxide, the same chemical process we recognize as rust. That bright layer reflects considerably more light, creating the planet's well-known rusty appearance when viewed from orbit. Where these contrasting materials meet, the boundary becomes more meaningful than a simple change in color. On one side lies relatively recent dust, deposited by winds over spans of millions of years. On the other rests volcanic ash, whose origins may reach back hundreds of millions, or even billions, of years to a period when Mars possessed a far more active interior. You can almost read that boundary like a page divided into two chapters. The brighter surface belongs to a younger stage in the planet's long evolution. Beneath and beyond it, the darker volcanic deposit preserves evidence from an age shaped by rising magma and widespread eruptions. Every advance of that dark margin therefore reveals more than changing scenery. It gradually uncovers another piece of an ancient world, exposing material that has remained part of Mars since an era when its interior still possessed enough energy to reshape the surface through fire. Scientists examining the comparison images eventually arrived at a striking conclusion. There were only two explanations that fit the observations well enough to deserve serious consideration. Both obey the known laws of physics. Both agree with what the cameras recorded, yet each tells a very different story about the surface beneath our gaze. The first possibility is surprisingly direct. The volcanic ash itself may be traveling. Fine particles, resting across the basin since eruptions hundreds of millions or even billions of years ago, could be lifted by Martian winds and carried gradually toward the south. Over many seasons, those tiny grains would settle onto neighboring terrain, expanding the visible boundary little by little until the change becomes measurable across decades. Under that interpretation, the dark region behaves less like a fixed deposit and more like a migrating blanket of volcanic material. Every grain would represent a fragment of ancient Mars beginning another journey after remaining in place for immense spans of time. If this explanation proves correct, you are left with an unavoidable question. What altered the environment enough for material that appeared stable for so long to begin shifting within the brief period of human observation? The second explanation turns the entire picture upside down. In this version, the ash never moved at all. Instead, the dark volcanic material may already extend across a much broader portion of Utopia Planitia, concealed beneath a remarkably thin covering of brighter reddish dust. Winds gradually remove that upper layer through a process known as deflation, meaning the steady stripping away of loose surface material by moving air. As the brighter coating disappears, the darker volcanic deposits below become exposed. Viewed from orbit, both situations produce nearly the same appearance. Freshly uncovered ash and newly deposited ash each create darker ground where lighter terrain once dominated. From hundreds of miles above Mars, distinguishing between those two outcomes becomes extraordinarily difficult. Each explanation also carries a deeper implication. Should the first hypothesis prove correct, then something within the planet's atmospheric circulation changed during the past several decades, while spacecraft were actively studying Mars. The shift may have unfolded slowly enough that nobody recognized it until two distant photographs were finally compared. The second possibility is equally remarkable. If the reddish covering is gradually retreating, then the visible patch may reveal only a small portion of a vastly larger volcanic deposit already waiting beneath the surface. As additional dust disappears through continuing deflation, more of that buried landscape would emerge into view without any volcanic material traveling at all. Neither answer provides an easy conclusion. One suggests that present-day Mars is changing in ways our observations have not yet fully explained. The other suggests the planet has concealed a much larger volcanic record beneath an unexpectedly delicate veil of dust, revealing it only as winds slowly reshape the surface. For now, both ideas remain firmly grounded in science, and both remind us that even after decades of exploration, Mars continues to preserve mysteries capable of resisting our best explanations. At first, the explanation seems impossible. How can a world wrapped in such an extremely thin atmosphere reshape its own surface at all? If the air above Mars carries only a tiny fraction of the pressure found at Earth's sea level, what gives its winds enough strength to redraw the outline of an ancient volcanic deposit? Near the Martian surface, atmospheric pressure averages only about 0.6% of that experienced at sea level on Earth. It resembles the conditions you would encounter nearly 22 miles above our own planet. Air that thin exerts remarkably little force. If you could somehow stand there without a protective suit, a passing breeze would feel surprisingly weak despite its speed. Yet the evidence tells another story. Mars supports active dune fields stretching across broad regions. Dark wind streaks appear, fade, and return over periods of weeks or months. Dust blankets, spacecraft hardware, softens exposed rock and occasionally engulfs the entire planet. Over immense spans of time, even cliffs have been gradually sculpted by moving particles carried through the atmosphere. The apparent contradiction begins to disappear once we consider the size of those particles. Much of the finest Martian dust measures less than 2 microns across, smaller than the width of a human red blood cell. Volcanic ash can be similarly delicate. Material this small requires surprisingly little force to become airborne. Winds blowing between 20 and 40 miles per hour can provide enough energy to lift these grains from the surface, even within such a rarefied atmosphere. Once the particles begin moving, Mars offers very few obstacles to slow them down. Earth constantly interrupts its own winds. Oceans exchange heat with the air. Forests and grasslands create drag near the ground. Moisture causes particles to clump together. Mountain ranges redirect entire weather systems. Mars lacks nearly all of those influences. Across broad open plains, moving air can continue traveling over extraordinary distances with comparatively little interruption. Sometimes those winds grow into events visible from space. Roughly 3 times during every Martian decade, regional storms expand until dust surrounds nearly the entire planet. Fine material rises as high as 25 miles above the surface before circulating around the globe. These planet-wide storms may persist for months, changing the appearance of Mars even while its underlying landscape remains the same. One such event unfolded during 2018. Dust became so widespread that sunlight reaching the solar panels of the Opportunity rover fell below the level needed to recharge its batteries. After operating successfully for 14 years, the rover exhausted its remaining power and never communicated again. Between the Viking observations and the later images captured by the European Space Agency, Mars experienced multiple global dust storms of this scale. Each one almost certainly transported enormous quantities of fine material across Utopia Planitia. Whether those repeated journeys carried ancient volcanic ash into new territory or gradually stripped away brighter dust from ground already hiding beneath it remains uncertain. That uncertainty is precisely why the changing boundary continues to command such careful attention. Long before the dark material became a scientific puzzle, it began as molten rock rising from the interior of a very different Mars. To understand the ash resting across Utopia Planitia, we have to picture a planet whose surface was shaped by fire on a scale unmatched anywhere else in the solar system. Most of that volcanic story centers on a single region known as Tharsis. This immense volcanic plateau spreads across roughly 3,000 miles of the western hemisphere and stands about 6 miles above the surrounding terrain. Rather than a single mountain, it is an elevated province containing several colossal volcanoes, each built through repeated eruptions over extraordinary spans of time. Dominating them all is Olympus Mons. From the neighboring plains, its summit rises about 16 miles into the Martian sky. For comparison, Mount Everest reaches roughly 5.5 miles above sea level on Earth. Olympus Mons towers nearly 3 times higher. Its broad base stretches approximately 374 miles across, covering an area comparable to the entire state of Arizona. Standing near its center, you would never see the opposite edge. The gentle slopes disappear beyond the horizon long before they reveal the mountain's full size. Such dimensions were possible because Mars developed differently from Earth. Our planet constantly rearranges its outer shell through plate tectonics, the slow movement of enormous slabs of crust. As those plates drift, volcanoes gradually migrate away from the deep source of magma feeding them. The Hawaiian Islands illustrate this process beautifully. One volcano grows for a time, then the moving crust carries it away, while a younger volcano begins forming above the same hotspot. Mars never adopted that pattern. Its crust remained largely fixed over deep reservoirs of molten rock. Instead of shifting away, volcanoes stayed anchored above their magma source for billions of years. Each eruption added another layer of lava to the same location. Growth continued with remarkable persistence, allowing mountains to expand far beyond anything Earth can produce through similar volcanic processes. The pace itself was often less dramatic than many people imagine. Individual eruptions may have unfolded much more gradually than those commonly seen on Earth, yet the accumulation never truly relocated. Layer rested upon layer through unimaginable stretches of time. Patience, more than violence alone, built the largest volcanoes in the solar system. Crater studies of Olympus Mons reveal another intriguing detail. Some of its youngest lava flows appear to be only about 25 million years old, remarkably recent in geological terms. Because of that evidence, several researchers describe the volcano as dormant rather than extinct, suggesting its volcanic story may not be completely finished. The ash spread across Utopia Planitia almost certainly did not erupt directly from Olympus Mons itself. Its precise volcanic birthplace remains uncertain. Even so, it belongs to the same broad era of Martian volcanism that raised the Tharsis Plateau and constructed those immense shield volcanoes. Every dark grain scattered across the basin carries the legacy of that ancient age, preserving material forged deep within Mars before rising to the surface and remaining there across the passage of billions of years. Imagine a planet becoming so burdened by its own volcanoes that the weight changes the orientation of the world itself. That sounds almost impossible, yet many planetary scientists believe Mars experienced exactly such an event, one that permanently altered landscapes thousands of miles away from the mountains that caused it. The source of that immense strain was Tharsis. Over billions of years, repeated volcanic eruptions piled lava upon lava until the plateau became one of the largest volcanic structures in the solar system. Its tremendous mass pressed downward on the crust, creating a gravitational influence that extended far beyond the towering volcanoes rising above it. Mars did not simply support that weight. It gradually responded to it. Around 3 billion years ago, the accumulated stress appears to have reached a critical point. Geological evidence suggests that the crust and upper mantle shifted together relative to the deeper interior by roughly 20 degrees. Scientists call this process true polar wander. In plain language, the solid outer shell changed its orientation while the deeper portions of the planet remained comparatively stable. The globe did not tumble through space. Instead, its outer layers slowly rotated into a new position over geological time. That movement reshaped the entire planet. River systems that once followed established paths found themselves flowing across landscapes with different slopes. Regions migrated closer to the poles or farther toward the equator, altering long-term climate patterns across vast distances. Even ancient coastlines recorded the consequences of that planetary adjustment. For many years, those coastlines puzzled researchers. Proposed shorelines surrounding the northern lowlands refused to follow the smooth, level contours expected from an ancient ocean. Their elevations rose and fell in ways that seemed inconsistent with standing water. Because of those irregularities, many scientists questioned whether a true ocean had ever existed on Mars at all. The concept of true polar wander offered a remarkably elegant explanation. If the shorelines formed first and the crust shifted afterward, the original waterline would no longer remain level. The planet itself had gradually deformed beneath the preserved coastal features, bending them into the uneven patterns observed from orbit. Rather than weakening the case for an ancient ocean, those distorted contours became evidence supporting both the ocean and the later reorientation of the planet. Utopia Planitia also fits naturally into this broader story. Positioned almost opposite Tharsis, the basin occupied one of the deepest regions of the northern lowlands. As the crust adjusted, its relationship to surrounding terrain changed as well, helping concentrate water sediments, and later geological deposits within this enormous depression. Its importance grew through the combined effects of impact, climate, volcanism, and planetary deformation. When you consider the dark volcanic material resting across the basin today, it becomes part of that sequence rather than an isolated feature. Some ash likely settled before the crust completed its gradual shift. Additional deposits probably arrived afterward. Beneath every visible layer lies the imprint of a world whose very shape changed under the weight of its own volcanoes, leaving that extraordinary event permanently recorded within the ground we continue studying today. There is one more layer beneath everything we have explored, one that transforms Utopia Planitia from a volcanic basin into something even more remarkable. Long before drifting dust, before exposed ash, and before the crust gradually shifted beneath ancient landscapes, this immense depression held an ocean that endured for hundreds of millions of years. The idea once seemed difficult to accept. Scientists identified possible shorelines, broad northern lowlands, and geological clues suggesting a vast body of water, yet the evidence remained incomplete. Over the years, additional observations arrived from orbit, each contributing another piece to the picture. Rather than depending upon a single discovery, the case gradually strengthened through multiple independent lines of evidence pointing toward the same conclusion. One of the most significant advances came during 2021 when China's Tianwen-1 mission delivered the Zhurong rover safely into Utopia Planitia. Unlike orbiting spacecraft, Zhurong explored the basin directly. Beneath its wheels, ground-penetrating radar, an instrument that sends radio waves into the subsurface and measures their returning echoes, examined buried layers extending roughly 260 feet below the surface. Those hidden layers displayed a remarkably familiar arrangement. They dipped gently toward the center of the basin, forming broad, repeating patterns closely matching coastal sediments found beside ancient shorelines on Earth. When waves and currents carry sand and finer material into standing water, the deposits settle into gently inclined layers over long periods. Volcanic eruptions produce different internal structures. Wind-shaped dunes create different geometries as well. The arrangement detected beneath Utopia Planitia corresponded most closely with sediments accumulating beside a persistent body of water. Further analysis published during 2025 strengthened that interpretation. Researchers studying the Zhurong observations concluded that the rover had encountered the remains of an ancient beach preserved beneath the Martian surface for approximately 3.5 billion years. The shoreline itself had disappeared from view long ago, yet its internal structure endured beneath younger deposits, waiting for radar capable of revealing it. Current estimates suggest this northern ocean spread into Utopia Planitia around 3,680 million years ago. At its greatest extent, it may have covered nearly one-third of the planet, making it at least comparable in area to Earth's Arctic Ocean. Average depths may have approached 3.5 miles before changing climate gradually transformed the environment. Over geological time, the water froze, retreated, or escaped into space, leaving the basin dramatically different from the one that had once collected waves along its margins. Its disappearance was never entirely complete. Large quantities of that ancient water remain preserved beneath the ground as buried ice. Earlier observations had already revealed extensive subsurface ice within Utopia, Planitia, and the evidence from Zhurong now places that frozen reservoir within the broader history of an ocean that once occupied this enormous basin. The expanding dark region therefore lies above far more than volcanic deposits. It also rests upon the preserved remains of one of the largest bodies of water ever known to exist on Mars. Far beneath the changing surface of Utopia Planitia lies another discovery that transformed how scientists view this region. The expanding dark deposit does not rest upon ordinary ground alone. Beneath the volcanic material, beneath the reddish dust, and beneath layers of ancient sediment, an immense reserve of frozen water has remained preserved for billions of years. During 2016, researchers studying observations from the National Aeronautics and Space Administration Mars Reconnaissance Orbiter examined radar measurements collected by the Shallow Radar Instrument. Ground-penetrating radar works by transmitting radio waves into the surface and recording the echoes returning from buried layers. This instrument can investigate structures extending roughly 1/2 mile below the ground, revealing features completely hidden from cameras orbiting overhead. Those echoes revealed an astonishing deposit beneath western Utopia Planitia. Buried below rock and sediment lay water ice covering approximately 145,000 square miles, an area larger than the state of New Mexico. The frozen layers ranged from roughly 260 feet to 560 feet thick. Altogether, researchers estimated that this single deposit could contain as much as 14,300 cubic miles of water ice, a volume comparable to Lake Superior. This is very different from the bright polar ice caps that immediately come to mind when we picture frozen worlds. The deposit never appears at the surface as broad sheets of exposed ice. Instead, it remains sealed beneath protective layers of soil, dust, and rocky debris. Many scientists interpret it as a surviving remnant of the ancient Northern Ocean, compressed, buried, and preserved through immense stretches of Martian history. The landscape above that hidden reservoir carries subtle clues to what lies underneath. Images collected by the European Space Agency reveal numerous scalloped depressions scattered across the basin. These broad, rimless hollows possess steep walls facing the poles and more gradual slopes facing the equator, creating shapes resembling the curved edge of a scallop shell. Comparable landforms occur in Earth's Arctic regions, where buried ice slowly changes directly into vapor, a process known as sublimation, leaving the overlying ground to settle downward. Across neighboring terrain, another pattern appears. Networks of cracks divide the surface into repeating polygons that resemble giant honeycombs stretching across the plains. Similar features develop within terrestrial permafrost as extreme seasonal temperature changes repeatedly contract frozen ground, opening fractures that return year after year. Both of these landforms appear within the same broad region containing the expanding dark material. In several locations, they can even be observed inside portions of the dark deposit itself. That relationship gives the surface an added layer of significance. The volcanic ash is not advancing across an empty plain carved only by wind. It occupies terrain directly over one of the largest known buried ice deposits on Mars, preserving the remains of an ancient ocean beneath a landscape where volcanic history, frozen water, and modern surface change all meet within the same extraordinary basin. The ground beneath the expanding dark deposit is changing as well, although at a pace almost impossible to recognize within a human lifetime. While winds reshape the surface above, another process unfolds beneath it, measured not in seasons or decades, but across immense stretches of Martian history. Together, these overlapping changes make Utopia Planitia one of the most dynamic landscapes on the planet. The broad, scalloped depressions scattered across the basin did not appear overnight. Their formation begins underground, where buried ice gradually transforms directly from a solid into a gas without becoming liquid first. Scientists call this process sublimation. As the frozen material slowly disappears, empty space develops below the surface. The overlying sediments eventually settle downward, producing the shallow, curved hollows visible from orbit. These depressions display a surprisingly consistent pattern. Their steeper walls most often face the poles, while their gentler slopes point toward the equator. Climate models indicate those pole-facing walls receive the greatest amount of solar heating during the Martian summer under the local seasonal geometry, allowing sublimation beneath them to proceed more efficiently than elsewhere. Over long intervals, the ground gradually sinks as support from the buried ice diminishes. Nothing dramatic happens in a single year. Instead, grains of dust and volcanic material slowly adjust to changing ground beneath them. The landscape is continuously reorganizing itself through countless tiny movements, each far too small to notice alone, yet together capable of reshaping entire regions over geological time. Another factor adds even greater complexity. Unlike Earth, whose rotation is stabilized by the gravitational influence of its large moon, Mars possesses no comparable companion. As a result, the angle between its rotational axis and its orbit has wandered dramatically through the ages. Geological studies suggest that this axial tilt has varied from roughly 10 degrees to nearly 60 degrees during different periods of Martian history. Those changing angles transformed the planet's climate. During intervals of higher axial tilt, the polar regions received increased sunlight. Ice that had accumulated near the poles gradually sublimated into the atmosphere before eventually returning to the surface as snowfall across lower latitudes, including broad portions of Utopia Planitia. Later, as the tilt shifted once again, those patterns changed, preserving layer upon layer of frozen deposits beneath the basin. The buried ice identified today may therefore represent the combined record of many separate climate cycles rather than a single frozen episode. Each period added new material, removed some of what already existed, and left another chapter within the subsurface waiting to be uncovered. Viewed together, the surface becomes remarkably intricate. Above, dark volcanic material continues changing its visible extent through processes that scientists are still attempting to distinguish. Below, ancient ice gradually retreats wherever sublimation removes support from beneath the ground. These are separate mechanisms operating across different timescales, yet they occupy the same landscape, making the expanding dark region part of a far more complex geological system than its appearance alone would ever suggest. Along the left edge of the same orbital image that reveals the expanding dark region, another feature stretches across the landscape with far less attention. It does not stand above the surrounding plains. Instead, it cuts into them. Long, narrow depressions intersect one another in broad geometric patterns, preserving another chapter of Utopia Planitia's history beneath the passing dust. These structures are known as grabens, a term derived from a German word meaning ditch. A graben forms when the crust is pulled apart, creating two nearly parallel faults. The block of ground caught between those faults gradually drops lower than the surrounding terrain, leaving behind an elongated trench. In this part of Mars, many of these depressions extend roughly 12 miles in length, while measuring just over 1 mile across. Viewed from orbit, they resemble carefully drawn lines crossing the basin floor before joining one another at broad angles. Their origin remains the subject of active scientific discussion. One possibility begins while the ancient ocean still occupied Utopia Planitia. Over immense spans of time, rivers carried mud, silt, and other fine sediments into standing water, where they slowly accumulated across the basin floor. As those deposits compacted and later dried, the surface fractured under changing conditions, leaving networks of cracks preserved within the hardened sediments. Comparable fracture systems have been identified beneath modern marine sediments on Earth, where sonar has revealed similar geometric patterns hidden below the seafloor. Another explanation places their formation after the ocean had already disappeared. When vast quantities of water covered the northern lowlands, the tremendous weight pressed downward on the crust beneath. Once that water was lost through freezing, escape into space, or other long-term planetary processes, the pressure gradually diminished. The crust responded by slowly rebounding upward. As those stresses redistributed through the surface, fractures opened, and sections of ground settled between parallel faults, producing the grabens observed today. Although these ideas differ in timing, they point toward the same remarkable conclusion. Whether the fractures developed while water still covered the basin or after its departure, they preserve the physical consequences of an ancient ocean. The cracks exist because water once played a defining role in shaping this landscape. They record either the conditions beneath that sea or the adjustment that followed its disappearance. The relationship between these trenches and the expanding dark material is especially intriguing. In several locations, the darker volcanic deposits extend into the grabens or gather along their margins, settling within depressions that have existed for billions of years. You can almost read the sequence directly from orbit. Ancient water helped shape the fractures. Geological forces preserved them across deep time. Now, the remnants of long-forgotten volcanism are collecting within those same openings, bringing together the records of vanished oceans and ancient fire across a single stretch of the Martian plain. Maps of the expanding dark region reveal a subtle detail that is easy to overlook at first glance. The boundary has certainly changed, yet it has not expanded evenly across the surrounding landscape. Instead, the most noticeable advance has been toward the south. That directional preference may be one of the strongest clues scientists possess, even though its full meaning remains unresolved. If the material behaved like a liquid spreading across level ground, you would expect growth in nearly every direction at roughly comparable rates. The observations show something different. Certain portions of the southern edge have migrated much farther than neighboring sections, while other boundaries have changed comparatively little. The pattern suggests that a persistent environmental influence has been guiding the process over many decades. Mars possesses recognizable seasons despite its thin atmosphere. A single Martian year lasts approximately 687 Earth days. As the seasons progress, carbon dioxide freezes onto the winter polar ice cap before returning directly to the atmosphere through sublimation when sunlight returns. Those seasonal exchanges alter atmospheric pressure across the planet, driving broad circulation patterns that repeat year after year. Climate models indicate that these large-scale circulation systems can generate a southward component to surface winds across parts of the northern hemisphere during particular seasons. If fine volcanic particles are truly migrating across the landscape, those recurring winds could gradually favor movement toward the south instead of producing an even outward expansion. The shape of Utopia Planitia introduces another layer of complexity. This enormous basin is far from a perfectly smooth depression. Subtle differences in elevation extend across its interior for hundreds of miles. Air descending into such terrain does not necessarily behave the same way it would above an open plain. Local circulation can strengthen weaken, or redirect regional winds, creating patterns that broad planetary models cannot always reproduce in fine detail. That possibility matches another important observation. Even along the southern margin, movement has not occurred uniformly. Some stretches of the boundary have advanced substantially farther than others over the same period of observation. Such variation suggests that local conditions differ from one part of the basin to another, influencing how surface materials respond over time. Several explanations remain scientifically plausible. Winds may be transporting dark volcanic particles toward the south. They may instead be removing brighter surface dust more efficiently along that margin, exposing older material already present below. A more intricate interaction between atmospheric circulation and basin topography could also produce the same overall pattern without relying upon only one process. For now, the direction itself remains one of the clearest pieces of evidence available. It points toward a controlling mechanism that researchers have not yet fully explained. Future atmospheric models capable of resolving much smaller regional air currents may eventually clarify the process. A lander operating within the advancing boundary could provide another valuable perspective by measuring winds directly where this slow transformation continues across the floor of Utopia Planitia. After everything we have explored, you might naturally wonder why this question still has no definitive answer. Mars has been under close observation for half a century. Numerous orbiters have mapped its surface, and modern cameras can resolve features only a few dozen feet across. Why, then, does the expanding dark region remain an unsolved problem? The first challenge is time itself. The boundary has shifted by only a few miles during an average Earth year. That amount of movement is effectively invisible during any single orbital pass. The change emerges only when images separated by decades are carefully compared. Even then, researchers must account for differences in seasonal dust, variations in the angle of sunlight, and subtle differences in camera calibration between spacecraft built generations apart. Every comparison contains uncertainty before any scientific interpretation even begins. A second difficulty comes from the appearance of the surface. The two leading explanations produce nearly identical results when viewed from orbit. If fresh volcanic particles gradually spread across brighter terrain, the landscape becomes darker. If winds instead remove a thin layer of bright dust covering older volcanic deposits, the landscape also becomes darker. From hundreds of miles above the planet, those outcomes can look almost indistinguishable. Distinguishing between them requires measurements capable of identifying subtle differences in mineral composition or, even better, direct examination of the surface itself. Global dust storms introduce another complication. During the planet-wide storm of 2018, airborne dust obscured large portions of Mars for months, reducing the clarity of orbital observations across enormous areas. If the boundary changed during that interval or shortly afterward, separating genuine long-term movement from temporary atmospheric effects becomes exceptionally difficult. The decades between the Viking observations and more recent imagery almost certainly included several such global storms, each with the potential to alter the visible surface before the next clear observations became available. There is one limitation more important than all the others. No scientific instrument has ever operated within the dark deposit itself. Viking 2 landed on the brighter surrounding plains. The Zhurong rover explored lighter terrain farther north within Utopia Planitia. Orbiters have repeatedly flown overhead, collecting valuable images and radar measurements, yet none can scoop a handful of the dark material, examine individual grains beneath a microscope, or directly measure how particles move across the ground through changing seasons. That absence leaves every explanation resting upon indirect evidence. Researchers compare images, analyze spectra, model wines, and reconstruct geological history with impressive accuracy, yet the decisive measurement remains missing. A future lander positioned inside the dark region could sample the volcanic material, monitor local winds through successive seasons, and determine whether new particles are arriving or older deposits are gradually being uncovered. Until observations are made directly from the surface, the expanding boundary remains one of those rare Martian mysteries that orbit alone cannot completely resolve. After following the evidence across this remarkable basin, the discussion naturally grows larger than a single expanding dark deposit. It reaches into one of the oldest assumptions in planetary science. When we look at Mars today, are we truly looking at a world whose internal story has completely ended, or one that is merely unfolding at a pace almost beyond human observation? For much of the 20th century, the accepted answer seemed straightforward. Scientists concluded that Martian volcanism had ended roughly 500 million to 600 million years ago. The planet was believed to have cooled internally, its molten reservoirs exhausted, leaving behind a geological record that would change only through impacts, wind, and the slow effects of weathering. Mars became widely described as a fossil planet, a place whose major chapters had already been written. Over the past 2 decades, that picture has become less certain. Images returned by the European Space Agency high-resolution stereo camera have revealed volcanic surfaces whose ages appear surprisingly young. Studies of Olympus Mons and the Tharsis Montes indicate that portions of their summit calderas, volcanic depressions formed after magma chambers emptied, were resurfaced as recently as about 20 million years ago. Some individual volcanic vents may even record activity within the past 2 million years. That span is remarkably recent in geological terms. Around 2 million years ago, early members of our own genus were beginning to spread across Earth. While our distant ancestors were shaping simple stone tools, parts of Mars may still have experienced volcanic activity. Additional clues have arrived from an unexpected source. Certain Martian meteorites, blasted from the planet by ancient asteroid impacts before eventually reaching Earth, preserve chemical signatures showing that one volcanic province remained supplied by rising magma for at least 2 billion years. A magma plume is a long-lasting column of hot material ascending from deep within a planet. On Mars, such activity appears to have progressed at an extraordinarily gradual pace, with volcanic construction occurring roughly 1,000 times more slowly than comparable processes on Earth. That difference matters. A planet changing so gradually may produce eruptions separated by immense intervals and deposits thin enough to blend almost seamlessly into older volcanic terrain. From orbit, distinguishing a fresh layer of dark ash from ancient volcanic material already covering the ground could prove exceptionally difficult. No spacecraft has ever witnessed an active eruption on Mars. Even so, the absence of a confirmed observation does not establish that every volcanic system has permanently ceased. For this reason, many planetary scientists increasingly describe Mars as dormant rather than dead. The distinction is important. A dormant volcanic system retains the possibility of future activity, while a dead one has no realistic path toward renewed eruptions. The expanding dark region does not demonstrate that Mars is volcanically active today. Yet it occupies ancient volcanic terrain on a world whose interior may still retain more energy than once believed, reminding us that some planetary stories remain unfinished even after billions of years. Imagine standing within Utopia Planitia at the moment these volcanic particles first settled onto the ground. Almost everything surrounding you would belong to a Mars that no longer exists. The familiar cold desert of today had not yet fully emerged. Instead, the planet was passing through an era of profound geological and climatic activity that unfolded between roughly 4 billion, 100 million, and 3 billion years ago, during the Noachian and Hesperian periods. The atmosphere was substantially thicker than the thin envelope surrounding Mars today. Greater atmospheric pressure allowed liquid water to remain stable across parts of the surface under favorable conditions instead of disappearing almost immediately into vapor or ice. Temperatures still varied widely, yet some regions and seasons could sustain flowing water long enough to shape the landscape in lasting ways. Across the highlands, rivers carved branching valley networks that remain visible from orbit after billions of years. Water carried sediment across immense distances before delivering it into broad northern basins. Clouds gathered overhead. Weather reshaped the surface. Rainfall may have occurred during portions of this distant era, although scientists continue to debate how frequently it fell and under what conditions. Deep within the planet, volcanic systems remained vigorous. Vast lava flows spread across enormous regions, while explosive eruptions lofted ash high into the atmosphere before it gradually settled over the surrounding terrain. Minerals such as olivine and pyroxene crystallized from cooling magma, becoming part of the volcanic deposits that would eventually blanket portions of Utopia Planitia. Each grain preserved the chemical fingerprint of molten rock rising from the Martian interior. Mars also retained a stronger magnetic field than it possesses today. A planetary magnetic field acts like an invisible shield, helping deflect charged particles carried outward by the sunday. Although that protection was already weakening, it had not yet disappeared completely. Over time, as the magnetic field faded and the atmosphere steadily thinned, the planet became increasingly vulnerable to the solar wind, contributing to the gradual transformation of its climate. When you place these pieces together, the contrast becomes remarkable. The volcanic material now visible within the expanding dark region formed on a world with active volcanoes, flowing rivers, standing bodies of water, thicker air, and a climate capable of supporting conditions unimaginable across most of modern Mars. Today, those same particles continue their slow journey across Utopia Planitia. They drift above buried ice that once existed as liquid water, pass over fractures shaped by an ancient ocean, and move through a basin whose appearance has been rewritten repeatedly across billions of years. Every dark grain carries with it a fragment of that earlier planet, preserving evidence of an environment that vanished long ago, yet still leaves unmistakable traces across the surface we observe today. Long before the expanding dark deposit became visible from orbit, Utopia Planitia possessed another quality that continues to draw the attention of planetary scientists. It is one of the few places on Mars where several of the most important ingredients associated with life may have existed together for an extended period. That possibility deserves careful consideration, balanced by the equally important fact that no confirmed evidence of Martian life has ever been discovered. When researchers evaluate whether an ancient environment could have supported life as we understand it, they often begin with three broad requirements. The first is liquid water. The second is a source of chemical energy capable of driving biological processes. The third is sufficient time for complex chemistry to develop and persist. Geological evidence suggests that Utopia Planitia satisfied all three conditions between approximately 3,680,000,000 and 3,420,000,000 years ago. The ancient Northern Ocean provided the first requirement. At its greatest extent, water within this basin may have reached depths approaching 3½ miles. That water remained in contact with the rocky seafloor for hundreds of millions of years, allowing minerals and dissolved chemicals to circulate continuously between the crust and the ocean above. Volcanic activity supplied the second ingredient. The eruptions responsible for producing the ash preserved across the basin would also have heated underground water. As that heated water circulated through fractured rock, it could have formed hydrothermal systems, places where mineral-rich, superheated water rises through cracks before mixing with colder seawater. On Earth, hydrothermal vents support thriving communities of microorganisms and larger organisms without relying upon sunlight. Instead, life obtains energy from chemical reactions involving dissolved minerals emerging from the crust. Time completed the picture. The Northern Ocean appears to have endured for at least several hundred million years. That interval overlaps remarkably well with the earliest known evidence for microbial life on Earth, which dates to approximately 3,700,000,000 years ago. The comparison does not demonstrate that life developed on Mars, yet it shows that both planets possessed environments potentially suitable for simple organisms during broadly similar periods in their histories. Even so, the scientific record remains carefully restrained. No rover, lander, orbiter, meteorite, or laboratory analysis has produced a biosignature that the scientific community accepts as definitive evidence of past or present Martian life. A biosignature is a physical, chemical, or structural feature that can be confidently attributed to biological activity. Many intriguing observations have been proposed through the years, but none has met that demanding standard. What we can say with confidence is narrower, yet still remarkable. If life ever emerged anywhere on ancient Mars, Utopia Planitia belongs among the strongest candidates for where it might once have existed. Beneath the slowly shifting volcanic material, the buried sediments, mineral deposits, and ancient seafloor continue preserving the geological record of a place where liquid water, volcanic energy, and immense spans of time once came together on a world profoundly different from the Mars we know today. Among the minerals identified within the expanding dark deposit, one stands apart for a reason that is not immediately obvious. Its presence raises a question reaching far beyond the movement of dust or ash. That mineral is olivine, and its survival within Utopia Planitia has become an important clue in reconstructing the basin's ancient history. Olivine forms deep inside a planet, under extremely high temperatures, before volcanic activity carries it toward the surface. On Earth, it is abundant within the mantle, the thick rocky layer beneath the crust, yet comparatively uncommon at the surface. Once exposed to liquid water and oxygen for long periods, olivine readily begins to change. Chemical reactions gradually transform it into new minerals, including serpentine and several other secondary minerals produced through weathering. Given enough time in a persistently wet environment, fresh olivine rarely remains unchanged. Mars presents a striking contrast. Orbital observations have revealed widespread deposits of olivine across many regions of the planet. For years, that distribution has been regarded as evidence supporting a long history of dry surface conditions. If abundant liquid water had remained in contact with those volcanic rocks for extended periods, much of the olivine should have undergone chemical alteration billions of years ago. This is where Utopia Planitia becomes especially intriguing. Geological evidence strongly supports the existence of an ancient ocean occupying this basin. Yet spectral observations, measurements of reflected light used to identify surface minerals, indicate that olivine remains present within the dark volcanic material. You are left with two observations that each rest upon substantial evidence, yet they seem difficult to reconcile completely. Several explanations remain possible. One possibility is that much of the volcanic ash containing olivine arrived only after the ancient ocean had already retreated, allowing the mineral to remain largely unaltered in the dry environment that followed. Another proposal suggests that the ocean existed for a shorter interval or under colder conditions, reducing the rate at which chemical weathering transformed volcanic minerals. Researchers have also considered whether later eruptions deposited fresh, olivine-rich material across an already exposed basin floor long after standing water disappeared. Each explanation carries different implications for the sequence of events that shaped northern Mars. If the volcanic deposits are younger than the ocean, then volcanic activity persisted well beyond the basin's wettest chapter. If the deposits formed while water remained present, then the chemistry of that environment may have differed substantially from what many current models predict. For now, the intact olivine remains an unresolved chemical clue rather than a contradiction with a single accepted solution. It preserves evidence from deep, within the Martian interior, while resting upon terrain that records an ancient ocean. Together, they suggest that the history of Utopia Planitia cannot be understood through one discovery alone. Its rocks, minerals, and landscapes must all be interpreted together, each preserving a different chapter from the same remarkably complex planetary story. Picture yourself standing where the brighter plains gradually give way to the darker volcanic surface. Every observation returned by orbiters, landers, and rovers allows scientists to reconstruct this place with remarkable confidence, even though no human footprints have ever reached it. The landscape stretches outward with very little interruption. Because Mars is smaller than Earth, its surface curves away more noticeably, bringing the horizon to only about 2 miles in every direction across the level plain. There are no forests, no mountains immediately ahead, and no moving water. Distance dominates your view. Above you, the sky is neither black nor blue. Fine iron oxide dust suspended within the atmosphere scatters sunlight into a pale butterscotch color. Closer to the horizon, the shade deepens toward tan as you look through a greater thickness of airborne dust. The sun remains visible, yet its warmth barely reaches the ground. An average daytime temperature near -80 degrees Fahrenheit leaves the surrounding terrain intensely cold despite the daylight. The atmosphere itself feels unfamiliar. It contains less than 1% of Earth's surface pressure, making every movement occur beneath a sky far thinner than anything experienced naturally on our own planet. Sound still travels through this air, although much less efficiently. Even a breeze approaching 20 miles per hour would produce only the faintest whisper, carrying remarkably little force against your suit. Looking behind you, the ground appears covered by reddish dust, broken occasionally by scattered rocks resting upon the plain. Polygonal patterns spread across portions of the surface, marking terrain fractured by repeated freezing and thawing in the distant past. Farther away, broad scalloped depressions interrupt the otherwise level landscape. Their gently sloping forms reveal where buried ice has slowly disappeared beneath the surface over immense spans of time. Now turn toward the advancing boundary. The change begins almost imperceptibly. Rust-colored dust becomes thinner, exposing isolated patches of darker ground beneath. A few steps farther, those patches connect until the volcanic material dominates nearly every direction ahead. Olivine and pyroxene rich deposits blanket the surface with a deeper reddish brown tone, creating a broad expanse that contrasts naturally with the brighter plains behind you. Nothing about this transition appears dramatic in a single moment. There is no towering cliff, no fracture opening beneath your feet, and no sharply painted line across the landscape. Yet the boundary beneath your boots represents one of the oldest exposed surfaces within Utopia Planitia. These volcanic materials originated during an ancient chapter of Martian history, endured the presence of an ocean, remained above buried ice, and continue responding to atmospheric processes that researchers are still working to understand. You would never watch the boundary advance with your own eyes. Its average movement of roughly 4 miles during an Earth year is far too gradual for direct perception. Even so, while you stood completely still, the landscape beneath you would already be participating in a transformation that has continued for decades and has likely been unfolding far longer than anyone first imagined. More than a century before spacecraft reached Mars, astronomers were already struggling to explain another spreading darkness across the planet. They had no orbiters, no landers, and no digital cameras. They relied entirely upon careful sketches made through telescopes, recording subtle changes that appeared from one Martian season to the next. Although their conclusions often proved incorrect, many of their observations were surprisingly accurate. During the 19th century, improvements in telescope design allowed observers to distinguish broad light and dark regions across the Martian surface. As the northern spring progressed into summer, many of the darker areas appeared to expand toward lower latitudes. Later, as autumn returned, those same regions seemed to contract once again. The cycle repeated often enough that astronomers recognized it as a genuine seasonal phenomenon rather than an isolated mistake. Among the most influential observers was Giovanni Schiaparelli. Throughout the 1870s and 1880s, he produced detailed maps assigning names to many visible surface features. He interpreted the broad, dark regions as permanent geographic provinces and referred to some elongated markings with the Italian word meaning channels. During translation, that word became closely associated with canals, encouraging a far more dramatic interpretation than Schiaparelli himself intended. Percival Lowell embraced that interpretation enthusiastically. He proposed that an advanced civilization had constructed an immense network carrying water across the drying planet. Modern observations have shown that these canals never existed. They resulted from the limited resolving power of telescopes combined with the remarkable tendency of the human visual system to connect scattered dark markings into continuous lines. Yet one important observation survived the collapse of the canal hypothesis. The seasonal darkening itself was real. Today, planetary scientists explain it through aeolian processes, a term describing the movement of surface material by wind. Bright iron oxide dust can accumulate over darker volcanic terrain, changing its appearance from orbit or through a telescope. Seasonal winds later remove portions of that dust, exposing the darker material beneath. As dust shifts again during later seasons, the cycle repeats across many regions of Mars. When you compare that long recognized process with the expanding boundary in Utopia Planitia, an intriguing connection emerges. Both involve the changing visibility of dark volcanic material beneath or alongside brighter dust. Both demonstrate that Martian winds can reshape the appearance of vast landscapes without requiring dramatic geological events. The resemblance also highlights an important difference. The seasonal dark wave, observed through telescopes, expanded and retreated within the rhythm of a single Martian year. The boundary in Utopia Planitia has behaved very differently. Its movement has remained predominantly southward across decades, rather than reversing with each changing season. That persistent direction suggests a controlling influence extending beyond the familiar annual dust cycle. The comparison reminds us that Mars has challenged observers across generations. 19th century astronomers correctly noticed a changing planet while misunderstanding its cause. Modern spacecraft have greatly improved our understanding, yet this slowly advancing dark boundary shows that even today, some Martian changes remain more difficult to explain than they first appear. Some mysteries persist because the necessary evidence does not exist. This is not one of them. The mechanism behind the expanding boundary in Utopia Planitia is, at least in principle, something planetary scientists know how to test. The greater challenge is placing the right instruments at precisely the location where the answers remain buried beneath the surface. One of the most valuable techniques begins far above Mars. Researchers measure thermal inertia, a property describing how quickly a material warms after sunrise and cools following sunset. Fine volcanic ash responds rapidly to changing temperatures because it stores relatively little heat. Solid bedrock behaves differently. Dense rock absorbs heat more gradually and releases it more slowly through the Martian night. By comparing temperatures across the boundary at different times of day, scientists can estimate whether the dark material forms a thin surface layer or represents exposed rock beneath disappearing dust. The National Aeronautics and Space Administration has already placed capable instruments into orbit. The Thermal Emission Imaging System aboard Mars Odyssey records infrared observations that reveal differences in surface temperature. The Compact Reconnaissance Imaging Spectrometer for Mars aboard the Mars Reconnaissance Orbiter measures reflected light across many wavelengths, allowing researchers to identify minerals exposed at the surface. Together, these instruments provide an extraordinary amount of information about the planet. Even so, neither has delivered a definitive answer for this particular boundary. Part of the difficulty lies in scale. If the volcanic material forms only a relatively thin covering above brighter ground, distinguishing that layer from orbit approaches the practical limits of current spatial resolution. Spatial resolution simply describes the smallest surface detail an instrument can separate into distinct features. Atmospheric dust drifting above Utopia, Planitia adds another complication by subtly influencing thermal measurements, making delicate differences more difficult to interpret with complete confidence. The most decisive evidence would come from the surface itself. Imagine a lander positioned directly across the advancing boundary with instruments capable of sampling material inch by inch beneath its landing site. A drill could determine whether the dark particles rest upon brighter sediment, whether volcanic grains extend downward through the upper soil, or whether the darker material continues, uninterrupted, below the visible surface. Laboratory instruments could measure grain size, mineral composition, layering, and the relationships between individual particles in ways impossible from orbit alone. At present, no active mission has been assigned specifically to investigate this expanding deposit. Future exploration plans, including robotic sampling efforts and eventual human expeditions, are likely to return attention to Utopia Planitia because of its remarkable concentration of geological questions. Until that happens, the slowly advancing boundary remains a scientific investigation conducted largely from hundreds of miles overhead, where remarkable instruments continue observing a puzzle that almost, but not quite, reveals its full story. A planet does not need erupting volcanoes or flowing rivers to remain active. Sometimes its changes unfold so gradually that they become visible only after years of patient observation. As our record of Mars has grown across more than 5 decades, an important picture has emerged. The surface is not frozen in time. It continues to evolve in measurable ways, often through processes operating at a pace very different from those on Earth. One of the clearest examples comes from fresh impact craters. Repeated imaging by the Mars Reconnaissance Orbiter has revealed new craters that were absent during earlier observations. Small meteoroids continue striking the planet, blasting away surface dust and exposing brighter material beneath. Around some impacts, dark ejecta spreads across the surrounding terrain where newly excavated debris has settled. In several cases, the impacts have uncovered buried water ice, appearing as striking blue-white patches in enhanced color images before gradually disappearing through sublimation over the following months. Scientists have watched this sequence unfold many times. Wind continues, reshaping the landscape as well. Active dune fields migrate across several regions of Mars, although their movement is measured in only a few feet during an Earth year. Within those dunes, smaller ripples often travel much faster, advancing by several dozen feet over the same interval. These motions confirm that even the planet's thin atmosphere remains capable of transporting sand and dust across surprisingly large distances given enough time. Elsewhere, steep crater walls undergo their own subtle transformations. Comparing orbital photographs taken years apart has revealed fresh landslides, dry flows of loose sediment, and dust avalanches descending along unstable slopes. These events occur without flowing liquid water. Instead, gravity steadily rearranges fractured rock and granular material whenever conditions become favorable for collapse. Near the poles, another cycle unfolds with remarkable regularity. During winter, carbon dioxide from the atmosphere freezes directly onto the surface, enlarging the polar caps by hundreds of miles. When spring returns, that frozen carbon dioxide changes directly back into gas, causing the ice margins to retreat once again. Decades of measurements have allowed scientists to model this seasonal rhythm with impressive accuracy, yet noticeable differences from one Martian year to another still remind us that the climate retains complexities beyond complete prediction. Against this broader background, the advancing boundary in Utopia Planitia appears less like an isolated curiosity and more like part of a living planetary system. Mars changes more gradually than Earth, yet gradual does not mean inactive. Fresh impacts expose hidden ice. Dunes migrate, slopes shift, polar caps breathe with the seasons. Across years, decades, and longer spans, still, the planet continues altering its own appearance. The expanding dark deposit belongs within that continuing story, reminding us that even a world often described as ancient still records new chapters every time we look closely enough. When the Viking missions arrived at Mars in 1976, they captured a world that seemed far simpler than the one we recognize today. Those first close views transformed speculation into observation, providing the earliest, sustained record of the Martian surface. Since then, humanity has launched more than 50 missions toward Mars, making it the most intensively explored planet beyond the Moon. Across those decades, our understanding has changed almost completely. Mars was once widely imagined as a dry, geologically exhausted landscape whose most important events belong to an unimaginably distant past. The accumulating evidence has revealed something richer. We now recognize a planet preserving nearly 4.5 billion years of history, including the traces of an ancient ocean, immense reservoirs of buried ice, comparable in volume to Earth's Great Lakes, volcanoes that may still be dormant rather than permanently extinct, a dynamic atmosphere shaped by seasonal cycles, and landscapes that continue changing slowly under present conditions. The expanding boundary in Utopia Planitia illustrates another lesson, one that extends well beyond Mars itself. The comparison between Viking observations and modern orbital imagery exists only because a camera recorded that particular stretch of ground nearly 50 years ago. At the time, no one expected that image would later become part of a long scientific investigation into a moving landscape. It was collected for entirely different reasons, yet its greatest value emerged decades after the spacecraft had completed its mission. That pattern appears repeatedly throughout planetary science. Transformative discoveries rarely arrive as isolated moments of revelation. More often, they emerge from patient comparison. Images are preserved, measurements accumulate. New observations are placed beside older ones until subtle differences become unmistakable. Only then does a process that once seemed invisible begin to reveal itself. The original Viking photograph did not capture a mystery, it captured a moment. The mystery appeared only after another spacecraft looked at the same place many years later and found that the surface no longer matched the earlier record. Without that first observation, there would have been no baseline against which change could be measured. You can think of every image collected from Mars today in much the same way. Each photograph freezes a single instant within a planetary history that continues unfolding whether anyone is watching or not. Many of those images will answer questions that scientists have not yet imagined asking. Others may become the essential reference for discoveries made long after today's orbiters have ended their work. The advancing dark region in Utopia Planitia belongs within that continuing archive. It is a record written across volcanic ground by persistent atmospheric processes that remain only partly understood. Its meaning has emerged because generations of spacecraft continued returning to the same world, looking again and again with greater precision, allowing time itself to become one of the most valuable scientific instruments ever sent to Mars. Perhaps the most valuable conclusion we can reach is also the simplest. After following the evidence across ancient coastlines, volcanic deposits, buried ice, orbital records, and decades of observation, we arrive at a boundary that marks more than a changing landscape. It marks the edge of present knowledge itself. There is much we can state with confidence. We know the dark region contains volcanic material, rich in minerals such as olivine and pyroxene. We know the boundary has shifted southward over the span of modern spacecraft exploration. We understand the broader geological setting that preserved these deposits within Utopia Planitia. We can also describe two physically reasonable explanations for the motion, one involving the gradual accumulation of darker material, the other involving the removal of brighter dust that conceals darker ground below. Beyond those conclusions, certainty becomes much more difficult. We do not yet know which process dominates the movement. We cannot say whether both mechanisms operate together, with their influence changing from place to place or from one decade to the next. The buried ice beneath the basin may interact with surface conditions in ways current observations cannot resolve. Even the volcanic minerals themselves preserve unanswered questions. Has the olivine experienced subtle chemical alteration during its immense residence within the basin, or does it remain remarkably similar to the material deposited millions of years ago? No existing measurement provides a complete answer. Neither can anyone describe exactly where the advancing boundary will lie 50 years from today. Rather than exposing a weakness, these unknowns reveal where scientific investigation is currently focused. Every major advance in our understanding of Mars has narrowed uncertainty in one area while uncovering new questions in another. Better instruments have not eliminated mystery. They have refined it, replacing broad speculation with precise problems that careful observation can eventually address. As you consider everything we have explored, the phrase, "we do not know," takes on a different meaning. It does not signal confusion or defeat, it reflects discipline. Scientists reach that conclusion only after eliminating explanations that no longer fit the evidence and identifying the questions that still require measurement. Confidence extends only as far as the observations allow. Any explanation presented today with complete certainty would reach beyond the available evidence. Mars has repeatedly demonstrated that patience produces stronger answers than haste. Observations continue. New images are collected. Better instruments are developed. Each returning spacecraft adds another page to a record that has been growing since the Viking missions first reached the planet. Meanwhile, the boundary continues its gradual advance across Utopia Planitia. Wind keeps reshaping the surface. Buried ice continues responding to the changing environment above it. Somewhere within those ongoing processes lies the measurement that will finally distinguish between possibility and demonstration. Until that day arrives, the most accurate description of this remarkable feature remains one that embraces both discovery and the limits of what we presently know. Long before either world carried familiar landscapes, Mars and Earth shared a common beginning. Both condensed from the same rotating cloud of gas and dust that surrounded the young sun approximately 4.5 billion years ago. During those earliest chapters, the differences between them were surprisingly modest. Each possessed widespread volcanism, each held liquid water upon its surface, each maintained a substantial atmosphere, and each generated a magnetic field deep within its interior. For roughly the first 100 million years, their histories unfolded along remarkably similar paths. Molten rock resurfaced vast regions. Impacts reshaped both planets. Water circulated across newly forming crust. If you could have observed them from a distance, separating their futures would have been difficult. Eventually, however, a single physical property began steering those futures apart. That property was mass. Earth contains roughly 10 times the mass of Mars. Because larger planets lose internal heat more slowly, Earth's deep interior remained hot for far longer. Beneath its solid crust, a liquid outer core composed largely of molten iron continues circulating today. Combined with Earth's rotation, that moving metal generates the global magnetic field surrounding our planet. The magnetic field acts as a protective shield, deflecting much of the charged material, continually streaming outward from the sunday. Mars followed a different course. With far less mass, its interior released heat more rapidly. Over time, the internal dynamo, the engine that generated its magnetic field, gradually ceased operating between approximately 4,200,000,000 and 3,700,000,000 years ago. Once that protection weakened, the solar wind, a continuous flow of electrically charged particles emitted by the sun, gained much greater access to the upper atmosphere. Across immense spans of time, portions of the Martian atmosphere escaped into space. As atmospheric pressure declined, conditions at the surface changed profoundly. Stable liquid water became increasingly difficult to maintain. Rivers disappeared, lakes diminished. The ancient ocean we explored earlier no longer remained sustainable beneath the thinning sky. Ice endured, but flowing water became an increasingly uncommon part of the planet's story. From that perspective, the contrast between Mars and Earth becomes remarkably direct. One world retained enough internal heat to preserve the processes supporting a long lived atmosphere. The other cooled beyond a critical point much earlier in its history. That divergence shaped every chapter that followed, from climate to geology, and ultimately to the environments each planet presents today. As we look outward across the solar system, this comparison offers a broader lesson. The air surrounding you, the oceans covering much of Earth's surface, and the uninterrupted chain of environments that allowed life to develop over billions of years all depend upon deep planetary processes hidden far beneath your feet. They trace back to the size of the world itself, a difference established during the birth of the solar system that continued influencing two neighboring planets long after their earliest similarities had faded. For almost all of Martian history, there was no observer. The processes shaping Utopia Planitia unfolded across immense spans of time, without a single eye to record them, no instrument to measure them, and no language capable of describing what was taking place. Long before the earliest human ancestors appeared on Earth, the surface of this basin was already changing according to the same physical laws that continue operating today. The advancing dark boundary almost certainly began its journey millions of years before anyone could have imagined another world beyond our own. Wind transported dust, volcanic grains shifted across the plain, buried ice gradually diminished where conditions allowed sublimation to occur. Broad scalloped depressions evolved a fraction at a time, while fractured ground remained etched across the basin. None of these changes required an audience. They simply continued, following the patient rhythm of planetary geology. If you could have stood there during those distant ages, nothing about the landscape would have suggested urgency. A human lifetime would have been far too brief to notice meaningful change. Even civilizations rising and falling on Earth would occupy only a tiny fraction of the interval during which this boundary continued its gradual migration. Mars measured time differently. Then something entirely new entered the story. On the third day of September in 1976, the Viking 2 mission transmitted images from Utopia Planitia after reaching the Martian surface. Around the same period, orbital observations documented the surrounding terrain in unprecedented detail. For the first time in the known history of the universe, a conscious mind recognized that this particular region existed. Scientists examined those images, preserved them, compared them, and unknowingly established the beginning of a record that future generations would revisit with far more advanced spacecraft. That moment did not alter the boundary itself. The dust continued moving. The volcanic deposits remained where physical forces carried them. Mars neither accelerated nor paused because someone had begun watching. What changed was humanity. A landscape that had existed for billions of years became part of our shared understanding of the solar system. Today, you are connected to that same chain of observation. A photograph collected nearly half a century ago can now be compared with modern orbital imagery from a world separated from Earth by tens of millions of miles. Across that interval, generations of engineers, scientists, and spacecraft have contributed individual observations, each one extending a record that no single mission could have completed alone. The difference between the age of this process and the length of our attention remains astonishing. We have observed only a tiny fragment of a story that began long before life emerged on Earth. In planetary terms, humanity has only just arrived, opening the first pages of a history already billions of years in progress, discovering that the chapter before us had been unfolding all along, whether anyone was there to witness it or not. Imagine that the remaining uncertainty surrounding Utopia Planitia disappears within the next decade. A carefully planned spacecraft lands beside the advancing boundary. Its instruments sample the dark material grain by grain. Weather sensors measure the local winds through changing seasons. A drill reaches beneath the surface, recovering layers that have remained undisturbed for millions of years. Laboratory analysis produces an unmistakable result, demonstrating exactly how the boundary has been moving and why it has continued advancing across the basin. That would answer one important question. It would also create many others. Every major investigation of Mars has followed this same pattern. A mystery is resolved with greater precision than anyone thought possible, and the solution exposes details no one previously knew existed. Fresh observations reshape old assumptions, while entirely new puzzles emerge from the evidence. Discovery on Mars has never reduced curiosity for very long. It has consistently redirected it. This is why describing Mars as a dead world has always been an incomplete shortcut rather than a complete scientific description. No one suggests that biological activity is transforming the planet today. Instead, the oversimplification lies in the word itself. Dead implies permanence, finality, and the absence of meaningful change. Yet the observations gathered across decades describe something more nuanced. Mars remains a planet where geological, atmospheric, and climatic processes continue operating according to the conditions that still exist. You have seen those conditions throughout this journey. Ancient volcanic material continues shifting across the landscape. Buried ice responds to seasonal and long-term environmental changes. Dust is transported from one place to another. Surface boundaries evolve. Impact craters appear unexpectedly. Polar deposits advance and retreat with remarkable regularity. Each process unfolds gradually, yet each leaves measurable evidence for anyone patient enough to compare one generation of observations with the next. Seen across billions of years, Mars appears to occupy a prolonged transition rather than a final destination. It began as a warmer world with active volcanism, flowing water, and a much denser atmosphere. Today it is colder, drier, and far more exposed to space after losing its global magnetic field. Even so, that transformation has not produced a motionless landscape. The planet continues responding to sunlight, gravity, wind, seasonal carbon dioxide cycles, and the steady arrival of meteoroids from interplanetary space. The expanding dark region within Utopia Planitia belongs naturally within that broader picture. Ancient volcanic deposits still participate in modern surface processes. Ice preserved from a distant climatic era continues interacting with present conditions. Atmospheric circulation, although far thinner than Earth's, remains capable of reshaping selected landscapes over decades of observation. Perhaps the most accurate description of Mars is neither dead nor active in the familiar terrestrial sense. It is a world continuing to evolve according to its own pace, preserving the memory of its distant past while steadily writing new changes across its surface, one patient year after another. Seen from orbit, the expanding dark region may appear to be only a stain upon the Martian surface. Yet when we gather together everything we have learned, its true significance becomes much larger than the moving boundary itself. It is a place where multiple chapters of planetary history overlap, allowing events separated by billions of years to occupy the same landscape at the same moment. The dark material traces back to eruptions that occurred hundreds of millions, and in many places billions, of years ago, during an era when Mars possessed abundant volcanic activity and a far denser atmosphere than today. Those eruptions happened before complex life emerged on Earth. They came before the first fish explored ancient seas, before amphibians reached land, and long before dinosaurs appeared. The volcanic grains moving across Utopia Planitia today began their journey before any animal had ever walked across our own planet. As those eruptions subsided, ash and fragmented volcanic debris settled across a basin that later became, or had already become, part of a vast northern ocean. That sea stretched across roughly one-third of Mars and reached depths approaching 3.5 miles in places. Beneath its waters, volcanic heat and chemical interactions created environments that scientists continue to examine as possible settings where simple forms of life might once have found favorable conditions. The ocean eventually vanished approximately 3,420,000,000 years ago. Water disappeared from the surface, while sediments gradually buried older volcanic deposits. Through repeated shifts in the planet's tilt, frozen water migrated across Mars, accumulating beneath the plains in enormous hidden reservoirs. Above those buried layers, dust continued gathering as one age slowly replaced another. At some point, whether within the last 50 years, the last several centuries, or even farther back, the boundary we have followed throughout this journey began advancing across the basin. Current observations cannot determine exactly when that motion started. They reveal only that it continues today, carrying ancient volcanic material across terrain that once formed the floor of an ocean and now conceals extensive deposits of buried ice. You are watching matter that has survived nearly the entire history of the solar system. Individual grains older than Earth's earliest animals are still participating in modern surface processes. They preserve memories of volcanic eruptions, ancient seas, climatic transformation, and the gradual cooling of an entire world, all while responding to present atmospheric conditions. That perspective changes the meaning of the dark patch itself. It becomes more than an unusual geological feature. It serves as a narrow opening into deep time, revealing how events separated by billions of years remain connected across a single landscape. Against those immense timescales, the whole span of recorded human civilization occupies only the briefest instant, while Mars continues preserving a history that reaches almost to the beginning of the solar system itself. As this journey draws to its natural resting point, one fact remains unchanged. The dark boundary in Utopia Planitia is still advancing. Current observations indicate an average movement of approximately 4 miles during each Earth year, generally toward the south. During the time you have spent listening, that immense feature has shifted by only a few inches, far too little for any spacecraft to notice in a single pass, yet entirely consistent with the long record assembled across decades. Years from now, another spacecraft, or perhaps a future explorer standing on the Martian surface, will examine this same region once again. New images will be placed beside those collected by the European Space Agency mission Mars Express during the year 2024. The comparison will reveal another chapter in the story. The boundary may have advanced another 200 miles. Scientists may finally understand the physical process responsible for its motion, or the landscape may present an outcome that no current model anticipates. Mars has earned a reputation for challenging expectations. Each generation of missions has answered important questions while uncovering others that no one knew to ask beforehand. There is little reason to imagine that this pattern has reached its conclusion. A world preserving billions of years of geological history still contains details beyond the reach of today's instruments. Some things, however, are unlikely to change. The volcanic material will remain unimaginably ancient. the frozen remnants of an ocean will continue resting beneath the plains. Scalloped depressions will deepen by almost imperceptible amounts as passing ages accumulate. The grabens will persist across the basin, preserving fractures created when this landscape experienced stresses almost beyond human imagination. Mars itself is approximately 4.5 billion years old. Whatever process is reshaping the dark boundary today almost certainly belongs to a story extending far beyond humanity's existence. It will continue after every spacecraft now circling the planet has completed its mission. The planet does not pause while we study it. It follows its own timetable. There is a certain perspective in recognizing that reality. The universe continues unfolding whether its workings are fully understood or not. Ancient worlds evolve according to physical laws that require no audience. Yet observation still matters, because every careful measurement expands the portion of reality that humanity can genuinely know. For a brief moment within that immense history, we have become participants rather than distant observers. We found the dark boundary. We compared photographs separated by generations. We traced volcanic eruptions, vanished seas, buried ice, and modern atmospheric change into a single connected narrative. Across 4.5 billion years of Martian history, our presence occupies only an instant. Even so, that instant allowed one small part of another world to become understood, however incompletely, by minds that evolved beneath an entirely different sky.